kinetics and equilibrium. So this question is providing us with an equation that represents the reaction between hydrogen and iodine. So we have H2 gas plus I2 gas in equilibrium with 2 moles of HI gas. They show us that there's a delta H of negative 10 kilojoules per mole that's associated with this forward reaction, right? So this is an exothermic reaction. Right off the bat, we can see that, right? Okay, so the next part of the question is saying the reaction is said to be in a state of equilibrium at a particular temperature and pressure. So now they're saying they want us to state 4 characteristics of a reaction that is in dynamic equilibrium. Okay, so we're just gonna outline some characteristics of a reaction that's in dynamic equilibrium. And so the first one that we're gonna say is that when a reaction is in dynamic equilibrium, molecules of reactants Okay, so this is our first statement of a reaction that's in dynamic equilibrium, is that the molecules of reactants are continually being converted into products. So these are continually being converted into products, and the molecules of products are continually being converted into reactants, right? And so that's kind of what these forward and backward arrow tells us, is that they're continually being converted, those molecules, right? Okay, so the second one is that at equilibrium, right, the rate of the forward reaction is equal to the rate of the backward reaction. Okay, so that's our second one. And the other one is that at equilibrium, so 3, which is our number 3, it says that at equilibrium, the concentration of reactants and products do not change. So those are constant. And then fourth, and finally, we say that the equilibrium only occurs in a closed system, right? And by a closed system, we mean that a system in which no particles are allowed to leave, none are allowed to enter. The system is closed, right? So these are our 4 characteristics of a reaction that's in dynamic equilibrium, okay? All right. So we're gonna clear that and move down. And down here, they're asking us to write the expression for the equilibrium constant in terms of partial pressures Kp for the reaction shown by the equation above. So again, this is our reaction here. We have hydrogen gas combining with iodine gas to give us 2 moles of HI gas. So it's a completely gas phase reaction. So we can use partial pressures to write our equilibrium constant. So that's what we're gonna do for 2 marks here. So let's get started on that, right? So Kp is gonna be, for the reaction shown above, is gonna be Kp is equal to the partial pressure of our product, which is HI. And because there are 2 moles of it, we're just going to square its partial pressure at equilibrium divided by the partial pressure of our H2 gas at equilibrium times the partial pressure of our I2 gas at equilibrium. Okay? So this is our equilibrium constant, or Kp, right, in terms of partial pressures. Okay? So that's that. All right. So the other question, part 3, saying state 2 factors which would not affect the equilibrium of the reaction shown by the equation above. So again, this is our reaction. Let me just jot it down here real quick. So it's just H2 gas plus I2 gas. And that yields, that's in equilibrium rather, with 2 moles of HI gas, right? So this question is asking us 2 factors that would not affect the equilibrium of the reaction. And one of the very first things that we can think of under any circumstance, something that would not affect any equilibrium, period, would be the addition of a catalyst, right? So if we add a catalyst, that's not going to affect the position of the equilibrium, right? So we can say catalyst, addition of a catalyst addition, let me just write that. Catalyst addition will not affect the equilibrium of that reaction. And then also, what also won't affect it is a change in pressure. Change in pressure will not affect the equilibrium of this particular reaction. So let me just get that down first, and then I'll explain why. Okay, if you change the pressure of the system, it would either want to go to the side where there are fewer molecules or where there are more molecules, depending on what's happening, right, in the given equation. In this particular equation, we have 2 moles total on the left-hand side, and we have 2 moles total on the right. So it's equal number of moles on both sides of this equation. And so as a result of that, right, or equal number of molecules on both sides of the equation. And so changing the pressure is not going to affect the equilibrium one way or another, because both sides would be favored equally. Okay? So the addition of a catalyst or a change in pressure is not going to affect the equilibrium of this reaction. Okay? So those are our 2 factors. So let's clear that and then go down. So the next part B, is asking us to describe the effect of decreasing the temperature, right? So this is what we're going to change. Now we're going to change the temperature and we're going to decrease it, right? Decrease the temperature from where it currently is. And they want us to know how that's going to affect the equilibrium of the reaction, and then how it's going to affect the value of Kp, right? So in the first case, so from up top, we knew that the reaction given is an exothermic one, right? So reaction is exothermic in the forward direction, right? So what that means is if we decrease the temperature, right? If we decrease the temperature, then the system is going to want to compensate for that decrease in temperature. And so equilibrium will shift towards the right. The forward. So in other words, what that means is that the forward reaction will be favored, right? So whichever reaction it is that gives off heat is going to be favored. And that's our forward one. It's the exothermic one, right? So the given reaction is exothermic in the forward direction. So if we decrease the temperature, right, of the system, then the equilibrium will shift towards the right. So the forward reaction will be favored, right? And so now let's move on to the value of Kp, right? And will decreasing the temperature affect the value of Kp, right? And so let's write what we had for Kp again. We said from up on the previous page, our Kp that we wrote down was Kp is equal to the partial pressure of Hi, right? All squared, so like all of this squared, divided by the partial pressure of H2 times the partial pressure of I2. So that was our Kp, right? So they're asking if the value of Kp is gonna change, right? And so there are two things that can change the value of an equilibrium constant. Well, there's one thing, and that's the temperature, right? If you change temperature, you're changing your equilibrium constant, no matter what kind of constant it is. If it's Kc, Ka, whatever the equilibrium constant is, as long as you're changing temperature, you're gonna change the value of that equilibrium constant. So yes, decreasing the temperature will affect the value of Kp. Right? It will affect it, but let's talk about how it's gonna affect it. So let me scroll up a little bit to give ourselves some more space here. Right? So, okay. We'll look at Kp, right? We're looking at Kp. Since we said that the forward reaction is the one that would be favored, right? We said that the forward reaction is the one that would be favored, right? In the forward reaction, when we're in the forward reaction stage, what we're preferring is the top, right? We're preferring the formation of Hi, right? So let me just kind of just jot that equation here again, just for completeness so we can see, right? I2 gas is going to be in equilibrium with that 2 moles of Hi gas, right? So when we drop the temperature, as we said, the equilibrium is going to shift to the right, and it's going to favor the production of these products. So let's write that. If we decrease the temperature, right, then the forward reaction is going to be favored. And so the partial pressure of your products, right, is going to go up. Right? So that's going to go up because we have a lot of this. And so by that same token then, because this is in the numerator and it's squared, if this partial pressure is going up, that means our Kp is also going up, right? So the value of Kp will increase. Okay? So just to recap, we drop the temperature, we favor the forward reaction, which produces a lot of Hi. Because the partial pressure of Hi is in our numerator here, and it goes as partial pressure of Hi squared, then that means that if we increase the partial pressure here by favoring the forward reaction, then what we're doing effectively is increasing our Kp, okay? So our final result then what we'll see is that we will see that the value of Kp increases, okay? So that's our final answer for that part. So we're ready to move on now. So I'm going to clear this and scroll down. Okay, so now we're at our calculation now. And they're saying that when 0.5 moles of hydrogen and 0.5 moles of iodine are allowed to reach equilibrium in a 1.00 dm cube flask at 500 degrees C and 1.01 times 10 to the 5 Newton meter squared, the amount of hydrogen iodide at equilibrium is 0.78 mole, okay? Calculate Kp at 500 degrees C if the total pressure is 1 Pascal. All right, so when we see all these words and all these things, the first thing that we have to do is reorient ourselves again. And to do that, the first thing that we're going to do is write the equation that governs this reaction that's taking place. And we did that up top, so let's write it again. It's going to be H2 gas plus I2 gas, and that's in equilibrium with 2 moles of HI gas, right? Let's also write our Kp again, since that's what they're asking us to calculate. Our expression for Kp that we got from up top was Kp is equal to the partial pressure of HI squared divided by the partial pressure of I2 times the partial pressure of HI. And these are all partial pressures at equilibrium, right? Because it's an equilibrium constant Kp, okay? So what we're gonna do now is that we're gonna construct a little ice table here to help us with this problem, okay? So we're gonna put our ice table here. So this is my initial, my change, and then my equilibrium values. And my reactants and products go here. So my reactants are H2, I2, and then my product would be the HI, right? One thing I want us to note right away is that the mole ratio is 1 to 1 to 2, right? So 1 molar H2 is going to get us 2 molar HI. 1 molar I is going to get us 2 moles of HI. So just keep that in mind, that that's our mole ratio. It's 1 to 1 to 2, right? So this is our mole ratio that governs this reaction. Let's just keep that there for now. Okay? All right, so let's go back to our ice table. They told us that initially we have 0.05 moles of hydrogen and 0.05 moles of iodine, right? So we're going to just write that here as our initial amount of H2 is 0.5, and for iodine it's 0.5. They also told us that at equilibrium we have 0.78 moles of hydrogen iodide, so we're going to just put that down here for hydrogen iodide, right? And of course, initially we don't have any hydrogen iodide because they didn't tell us that, right? Okay, so that's 0 initially, and then at the end, at equilibrium, we have 0.78 hydrogen iodide. So based on this 1 to 1 to 2 mole ratio, we know that over the course of the reaction, right, X moles of H2 will be used up. And so at equilibrium, we will just have 0.5 minus X. And then for I2, it's the same. It's a 1 mole ratio, 1 to 1 to 2. So we'll have 0.5, whatever we started with, minus what it changed by, right? And so that's for I2. And then for HI now, how is that gonna change? We're gonna end up forming two times however much of this we used up, right? So it would be plus 2 times X, right? Because it's a 1 to 1 to 2. So if we use up 1 mole of H2, we're gonna form 2 moles of HI. If we use up X moles of H2, we're gonna form 2X moles of HI. So that's where this 2X came from, right? All right. So what then remains, or what we can do right now, is that we know that we didn't have any HI initially, and in the end, we had 0.78, right? So right away, we know that whatever our changes is what we ended up with at equilibrium. So right away, what we can do is we can just kind of say, okay, we can solve for X right away, right? So 2X is equal to 0.78. So X is gonna then be equal to 0.78 divided by 2. And if we do that, what number are we gonna get? We're gonna get X, or that change is gonna be equal to 0.39. So that's what X is, right? That's what X is. All right. So then right away, we can calculate what this equilibrium moles of H2 and I2 would be by subtracting out the 0.39 from this. And so we'll end up getting let me just write out everything for completeness. It would be 0.5 minus 0.39. And it's the same thing for the iodine. So then we would end up with that being 0.11 for both of them, right? And that's our equilibrium moles. That's the number of moles of each of these that we have at equilibrium, right? So we know that at equilibrium, we have 0.11 moles of H2, 0.11 moles of I2, and then 0.78 moles of HI, right? So now we have to convert those moles into partial pressures, right? And so the way that we do that is so let's start with the HI. The partial pressure of HI, right, is going to be equal to the total pressure, which they told us was 1 Pascal, times the mole fraction of that HI at equilibrium. So the mole fraction would be the moles of HI, which is 0.78 divided by the total number of moles at equilibrium, and that's just 0.11. So let me just write that out for completeness. 0.11, that's the total moles that we're calculating there, right? 0.11 plus 0.11 plus 0.78. So this is just a mole fraction calculation, right? So PT is the total pressure, that's 1 Pascal, that's what they told us. So we're just multiplying that by the mole fraction of HI. And this is just 0.78 over 1, because 1 is the total mole fraction. So in the end, right, the partial pressure of HI is just going to end up being 0.78 Pascals, right? And so similarly, we can carry out a similar calculation for P, the partial pressure of H2. And so that would just be the total pressure, which is 1 Pascal, times the mole fraction of that HI, which is 0.11 over 1, because the total mole fraction is, the total number of moles is 1. So the mole fraction of HI will be 0.11 over 1, and then multiply that by the total pressure, will get us 0.11 Pascal for that. And of course, it's the same thing for the I, right? Because they have the exact same mole fraction. So Pi2 would be equal to 0.11 Pascals as well, right? So now all that remains is for us to plug in these partial pressure values into our Kp to be able to calculate the value of Kp at 500 degrees C, right? So let's just plug that in. I'm going to put this in a different color here. So then we're plugging in those numbers now, these numbers, right? So 0.78 is for HI. So we're going to put that up here. 0.78 for HI's partial pressure, and we have to square it. Remember, they squared here. Then we have to divide that now by the 0.11 for the I, and then the 0.11 for the H2. So that would be 0.11 times 0.11. Right, and when we do that, we're gonna get a value of, we plug that in our calculator, we're gonna end up getting 0.6084 divided by 0.0121, right? And that's gonna get us 50.2, right? Let me just come over here and just box that number. So Kp is then going to be equal to 50. So that's our final answer. So I'm just going to box that this is our Kp. Okay. So those are the steps that we go through. We have our balance equation. We write an expression for Kp. We use our ice table to come out with our moles. Then once we get our moles, we can come over here and then find the partial pressures, which is the total pressure that they gave us, times the mole fraction of the particular species that you're calculating that for. Right? So when we do that, we end up with these numbers here. And then all we're going to do is just plug these partial pressures into our Kp expression, and we'll come out with a value for Kp. And in this case, ended up being 50.2. Okay.